Hi, folks. In past videos, we talked about the infinite size of the natural numbers, the odds, the evens, and the integers. In this video, we're going to look at the infinite size of the rational numbers. What we want to know is whether or not this is the same size as the natural numbers, whether it's aleph naught as well. So here's the question for you. Are these two sets the same size? What I want you to do is pause your videos and try to decide if you think the answer is yes or no. Okay, that was your chance to pause your videos. Now, you might be convinced from all those other attempts that every infinite set has size aleph naught. And if that was where you were going, then you're right. This does have aleph naught size. So the answer is yes here. But there's a reason why I think that should be puzzling to us. Because the tricks, I wonder if you figured out how to do a one-to-one correspondence, even if you thought that was the right answer. Because it's really not obvious how this correspondence would go. The rational numbers have this bizarre property called density, which is really fascinating. Between any two fractions, there's another fraction. Like between a half and one, think about the fraction 3/4. Or between 3/4 and one, what about the fraction 7/8? And you can just keep going like that. There's always another number between them, which means, the integers were interesting because the ellipsis, the infinity for the integers, the positive and negative integers, trailed off in two directions, to the left and to the right. But the rational numbers, there's an infinity, there's a little ellipsis between every two of these things. There's an infinite number of numbers. Because, of course, if there's two numbers between any of them, if there's some number between any two of them, then there's going to be another number and another number. So there's really an infinity of numbers between any two of these rational numbers. And that makes it seem like it's impossible to create a one-to-one correspondence. There's just too many infinities, too many ellipses to ever pair these off with the natural numbers. At least that's a very natural thought. But as I told you, you can do it. It just takes a lot of ingenuity, and it's a beautiful proof. Here's the simplest way to do this proof. Think about the rational numbers can all be expressed as a fraction. And just remember your sort of grade school terminology. The numerator is the top part of the fraction. The denominator is the bottom part of the fraction. Let's make a grid like this of natural numbers. So zeros at the intersection here. So there's a column where the natural numbers go off for infinity, and then there's a row, all these rows where they go off for infinity. And what we do is if we make one of these things, and you can do it however you want. Let's just make this vertical part the numerators and this horizontal part the denominators. And then think about every point in this grid. Every one of these nodes is going to be a fraction. And it's going to look like this. So this would be 1/1. Or this is going to be 1/2. This is 1/3 because the numerator is on top of the denominator. And here we have this grid of all of these numbers. Now the red gives it away. There's a beautiful way of pairing all these things off in the grid with the natural numbers. Let's just sort of zigzag through this thing. And then everything in this grid is going to get paired with the natural numbers. And if you think about it, though, every rational number is going to appear on this grid because every rational number can be expressed as a fraction. So pick your favorite rational number, like 17/13. That's going to be over here. In fact, you know how to find it. Go down 17 parts and go over 13 nodes, and you're going to be there. So there's no rational number that doesn't appear on this grid, but everyone is going to get paired off with a natural number. It's beautiful. Now, there's actually one thing that's missing here. This is an almost perfect solution. Pause your videos and see if you can figure out what the problem is. This is not yet a one-to-one correspondence. It needs one tiny tweak. Okay, here's the answer. We just need to include 0 because 0 is also a rational number. It can be expressed by the fraction of 0/1 or 0/20. So this isn't, we have to make sure to pair 0 with something. Well, let's just pair 0 with 0 and then we'll just keep going. Here's 1 with 1, but 2 is going to be with 1/2. 3 is going to be with 2/1. And we're going to go like this. And now every rational number is going to get paired in a one-to-one correspondence with every natural number. And indeed, therefore, Q has the same size as N. They are both aleph naught. Okay, thanks.